Okay, so I think it's time to start this day of the conference with a talk by Tony Várilly-Alvarado, who will speak about quasi-hyperbolicity via explicit symmetric differentials.
All right. Thank you very much for the invitation, and thank you for coming in after last night's shenanigans. Yeah, I want to talk about a joint project with Nils Bruin, and it discusses sort of some old ideas that I guess I would say are classical because they're before my time, about how to sort of bound rational curves and genus 1 curves on surfaces of general type, and sort of bring those ideas a bit into the 21st century now that we have way more computing power than we did in the late 70s and early 80s when some of these ideas started coming out. So let me start by explaining sort of the simplest version of the idea on how to constrain rational curves. Okay, and this is sort of how we will do so by using algebraic differential equations, in fact. So this is an idea that goes back at least to Bogomolov and Green-Griffiths, but it already has intimations in all the work of Bloch as well. Okay, so x over c, this is going to be a smooth projective variety of dimension n. And I'm going to look at the sheaf of one forms on this. This is a locally free sheaf of rank n. And I'm going to construct from it its sort of associated projectivized bundle. So I'm going to draw a picture. And okay, so this is going to be x. And up here, I'm going to take p of this omega 1 x. And this is, I should say, this is the projective bundle of hyperplanes. So this bundle has more of a tangent bundle field than a cotangent bundle field to it. Okay, so, and this is going to be little x, and this map is going to be p. And what we're going to do is we're going to use the fact that there is a bijection between global sections of omega 1x and global sections on this projectivized bundle of the O of 1, the Grothendieck bundle that comes with this projective vector bundle. And so if I take some omega here, I'll denote the corresponding section, S omega, and by S omega 0, I'll mean the divisor of zeros. Of this S omega. And so what I want to do is I want to think of my omega as a section to this, and this is going to carve out for me this nice sort of divisor of zeros here. So this is going to be S omega 0. And what we'll do is we'll see what happens when I have a curve mapping into x and how that interacts with this S of omega 0. So what we'll do is we'll say that you have C, a smooth proper curve. so also over C, and that I have some map, some morphism from C into X, and I have my projectivized vector bundle, and with the map P. And it turns out that I can lift this up. I'll call this T sub F. And you can say roughly what this map is. So at least in the locus where F is unramified. So what do I have to do? Well, I'll have to tell you sort of a point in X, and then I have to give you, well, since this is the projective bundle of hyperplanes, what I'll want to do is I'll give you a tangent vector to the curve C, or the image of the curve C, at the image of my point X. Okay, and so this will be, f of X, and I'll take a v, and this v will be a non-zero vector, so tangent vector, to this f of c at f of x. Okay, so now, I mean, this is all sort of general, and now what I'm going to do is I'm going to say, okay, what if C is P1? Do we get a little bit more juice out of this? And so let's say that C is P1. And you can also say something if C is a curve of genus 1. But let me just stick to P1 for most of this talk. So then you have a map from P1 to X. And so pullback of differential 1 forms will give you a map from H0 of omega 1x to, well, H0 of omega P1. But this is all minus 2, right? And so this is 0. And so what happens is that in this case, if I take one of these global sections and I pull back, I get 0. And that means that when you take this TF of P1 up here in the projectivized vector bundle, it's going to have to sit inside the divisor of zeros of the corresponding section. And so it's going to, so my rational curve, the image of my rational curve is going to have to sit in here. And that can actually place a constraint on this rational curve. Right? And so why is that? By the way, if you sort of spell all of this out, this will look like an algebraic differential equation, this condition. Well, if you have just one section, then well, this P1 is somewhat constrained. But if you have lots of independent sections here, this condition is going to have to be true for all of those independent sections. And so this P1 is going to have to start lying at the intersection of a whole bunch of these surfaces. And that's really going to constrain where the rational curves can be, say if you push down to x. And so this is sort of a slight cartoon version of the idea. And then this can be really souped up to sort of higher jets and things like this. This is sort of the absolute simplest version. But let me just sort of show you an example. And this example is overkill. That's okay, because it illustrates the point that I'm trying to make. So say, for example, that x is an abelian variety. So in this case, if I take this vector space, this is going to be some g-dimensional vector space. And so I'll write omega 1 through omega g for global sections. And what will happen is that, as I was saying, this T1, a T of P1 is going to have to lie inside all of these divisors inside my projectivized vector bundle. And then, okay, so it takes a little calculation, but you can show that this is not possible. Okay, so, but really the point that I want to make is that sort of each one of these things is carving out some sort of red hypersurface up there, and these conditions all have to be satisfied simultaneously, so the image of this P1 has to be at the intersection of all of these red hypersurfaces. And so the conclusion here is that there are no non-constant maps from P1 to X. So, okay. Abelian varieties, there's many ways of showing that abelian varieties don't have rational curves. You could have said, well, such a map would have had to factor through the Albanese, and the Albanese is trivial. I mean, there's many ways of doing something like this, but I wanted to show you this because this strategy can be employed in many other contexts and not just abelian varieties. So the natural question here is, so what other varieties can we apply this to? Okay, so let me start. So I want to do surfaces, and I want to do mostly surfaces of general type. So a new section will be nodal surfaces. And in this case, there is a conjecture. This may be dangerous. Okay, so there is a conjecture. And this is, in various forms, has been put forth, for example, by Bogomolov, Green-Griffiths, Lang. And so it'll say that, so if I take X over C, a smooth projective surface of general type, then in fact, then X contains only finitely many curves of genus 0 or 1. Okay, and in this case we say, sorry? Yes. Yeah. So and we say that X is algebraically quasi-hyperbolic in this case. And the quasi is coming from the fact that you're saying finitely many as opposed to none. Okay, so if you want to say none, then you would call it algebraically hyperbolic. And so I'll abbreviate this by AQH. I won't use the abbreviation very much, but I thought I should put it there. So for example, I can take X to be in P3 to be a smooth surface of degree at least 5. So those are all surfaces of general type. And so one thing you could ask is, well, could we apply something like that idea to a surface of degree at least 5 and use that, because we might get some constraints on the locus where these rational curves and perhaps some of these genus 1 curves have to lie, and that might tell you, when you push that locus down, you might see, say, some closed subset of X. But sadly, this is not to be. So because for such an X, you can show that when you look at global sections of one differentials, this is trivial. So we can't use the above idea. Okay, and so, but you might say, well, I mean, okay, so omega 1 didn't work, but maybe you could use some other kind of vector bundle constructed from omega 1. So for example, you could take symmetric powers of omega 1. There are varieties out there which don't have global 1 forms, but they do have global symmetric 1 forms, so sort of polynomials of degree m on 1 forms. And you could try to do that, but that also doesn't work. You could try something like this, but the answer is nope. But now, here's the sort of the key idea. So the strategy seems sort of doomed to fail already, but Bogomolov and Oliveira revived it by saying, okay, well, maybe you don't have to take x to be smooth. Maybe you can allow x to be mildly singular. So this is Bogomolov and Oliveira in 06. And so try an x with very mild singularity. So this sing x is going to be a collection of L isolated nodes. So ordinary double points on your surface, and I'm going to call this locus S. And then you can take a minimal resolution, so don't blow up more than you have to. And you could try to look for symmetric differentials on y and apply this sort of strategy. Okay, so you can show sometimes, if you look at h0 of y of Sm omega 1y, then you find symmetric differentials for L and M sufficiently big. And when you find those differentials, you can apply the idea up there to actually show that y has to be algebraically quasi-hyperbolic, and therefore x will also have to be algebraically quasi-hyperbolic. So this implies that y and x are algebraically quasi-hyperbolic. Okay, so is this going to stop after? Oh yeah, great. Okay, so now that was 2, number 1, down. So what I want to do in this talk is to sort of start a conversation about an effective version of the results of Bogomolov and Oliveira, and also to point out that sort of as we were doing this project, we found sort of a few small bugs in the original paper of Bogomolov and Oliveira. It does not really affect the main result, which is that if L and M are sufficiently big, you know, it's basically what I wrote there. That is still correct, but it does affect sort of for what L and what M you might see differentials. And so part of this project was to straighten this point out, because you need something like that if you're trying to do more explicit calculations. So the kind of questions is that we want to answer is, well, okay, so for what, you know, x can we apply this to? Number 2 is sort of how large must this L and M be? And finally, if you managed, if you have a concrete surface, so the L is fixed, and you find out what the M is, can you run that original idea that I spoke about in the first few minutes of the talk and actually bound the locus of rational curves and genus 1 curves? So can we bound the locus of rational curves? And so, for example, the kind of thing that we'd like to say is, okay, here's a very concrete surface of general type that's somewhat nodal, and it looks very complicated, but there are at most 700,000 rational curves on it. Okay, and that's the sort of thing that you get. Okay, so the bounds, I'll try to be very precise about why our bounds are not necessarily sharp. There's room for improvement, but it needs a new idea, and this is part of what I want to put out there. So, okay, so the setup. So we're going to do complete intersections, and so this X, this is going to be a surface. It's going to be a complete intersection. Of type D1 through Dn minus 2 in Pn. And so what I mean by this is that it's the intersection of n minus 2 hypersurfaces, the first one of degree D1, the next one of degree D2, and so on. And two things. One, it'll be slightly nodal, so just as before. So these are nodes. So nice ordinary double points, which we call S again. And okay, very important. I want to be in the realm where my surface is of general type. So I'll want that the sum of these degrees is greater than n plus 1. So for example, you could take a degree 5 surface in P3, okay, or a degree D surface in P3 where D is greater or equal to 5 if you want. And so what we want to do is we want to take a minimal resolution of this. So blow up these nodes. And then we want to investigate whether this resolution has symmetric differentials. So we're going to take this y e over x s. Okay, so this is, I blow up my nodes, and here's my exceptional divisor. This is going to be a minimal resolution. Okay, and so the goal is going to be to understand h0 of y sm omega 1y in terms of L and M. Okay, so that's what we want to do. And so the first thing we'll do is so we have a map, we have a sheaf, we have the Leray spectral sequence. So use the Leray spectral sequence for tau and this Sm omega 1y plus some work of Bogomolov and Oliveira in this paper that we checked pretty carefully. And you can deduce the following. So can deduce. There was a point when I first started preparing the talk that I actually thought about writing down the long exact sequence and explaining why all of these things vanish. And then I realized that it's probably a little too early in the morning to do that. So let me spare you the details, because I'd rather show you some interesting calculations and pictures at the end instead. So for m at least 3, you can show that the H2 of Sm omega 1y is equal to 0. That's good. That's not what we want. We want H0, but having a vanishing of H2 is good because it's going to start to allow me to use Euler characteristics instead of H0. And so, but if I want to use the Euler characteristics, I should also know something about H1. And so H1 of y Sm omega 1 is a sum of two things. So this is H1 of x of tau lower star of my symmetric differentials on y, plus H0 of x and R1 tau lower star of Sm omega 1y. Okay, and so let me push this up. This one. Okay, so with these two things in mind, then what I want to do is I want to replace the H0 of Sm omega 1y with the Euler characteristic plus the contribution that's coming from this H1, which we've separated into two terms. And I'm telling you this for a reason. I'll point it out in a second. So you can deduce from this that this H0 of omega Sm omega 1y is in fact, well, okay, so this is equal to the Euler characteristic of this thing plus the H1 because the H2 vanished. And of course, this is here, I'm assuming the condition so that the H1, the H2 vanishes. And then we're going to say that this is greater or equal to the Euler characteristic y plus. Okay, so here's the catch. If we could really understand those two terms, our results would be on the nose exact and instead of bounds. But one of these terms we don't understand very well. So, is it this one? Any guesses as to which one of these two is harder to understand? If you ask me, they both look terrible. So, that's right. Nobody understands H1. Very good, Dan. So, yeah, but here's the weird thing. We can compute this. Exactly. Yeah. So I also found it somewhat counterintuitive. I thought this was going to be hard, but you know, as Dan points out, H1 is hard as well. So all we're going to say is, well, this is a dimension of a vector space, so it's greater or equal to 0. And this is a horrific bound. So if we could understand more about this term, then our results would be somewhat improved. And part of what we want to do is we've sort of recast a bit of the Bogomolov Oliveira results to pinpoint exactly sort of where the bounds are not sharp. And so this is the term that is going to make things a little hard. Let me raise this back up again. And so what we'll have here is this H0 of x R1 tau lower star of Sm omega 1 y. Okay, so the good news is that this first part is actually not too difficult to compute. So the remember that, so x started out life as being nodal and y was a resolution, and we have to compute the Euler characteristic. But the really nice thing is that there's a result of a TIA from 1957 that says that you can compute this Euler characteristic by just pretending that y is in fact a smooth complete intersection of the right type. So this z is going to be a smooth complete intersection of type d1 through dn minus 2 in Pn. Okay? And so essentially, I mean, what the proof is trying to do is to put the singular x as a central fiber in some family, and then say that when you look at sort of a simultaneous minimal resolution of the fibers, they're actually pairwise diffeomorphic. And Euler characteristics are diffeomorphism invariants, so you may as well just pretend that y is in fact a smooth complete intersection of the right type. And then that's really good news, because this is just some Chern class calculation. And so if you had never done it, you just open Fulton's book and you read about the splitting principle, and then you play around for a little bit, and then you compute. So this is a Chern class calculation. And I will show you the result of this Chern class calculation, which is part of why this talk is a bit of a hybrid thing, because if I just wrote the result down, it may take the rest of the morning, I mean. Okay, excellent. So now, in our goal to understand why this minimal resolution, and you may or may not have symmetric differentials, we have a part that we can sort of reduce to known problems, and then there's this bit. And so we need to understand how to compute that bit. So let me move over to that. And this is where things get a little hairy. And we use some technology that I was unaware of, so I learned a lot. So computing this H0 of x R1 tau lower star of Sm omega 1 y. Okay, so the idea is we compute node by node. So you have to do a little argument here that the sheaf is really supported on the zero-dimensional locus where x is singular, and you can really sort of shrink things enough to try to look at that in a more local way and try to sort of add up the contributions of the different nodes. And then we use something called the local Euler characteristic. And this is a notion that I learned in a paper by Wall from 1993. Bogomolov and Oliveira already used this. This is not a new idea that we're bringing in. But we do separate the Euler characteristic a little bit. So, okay, so the setup. So this is a slight gear shift, okay? So x and y are going to start meaning slightly different things, and I'll try to keep very straight what they mean, okay? So, so this is little s, not capital S, one node, okay? And so the point is this should be an isolated, normal, complex, analytic surface singularity. And this should be what's called a good resolution, but that basically just means that E should be a simple normal crossings divisor. And I'm going to fix, so there's this and F, and this is going to be a locally free sheaf, coherent sheaf, so locally free coherent sheaf on Y. Okay, so let me put this up, this down. Oh, no. So the local Euler characteristic of the sheaf Y for this singularity, so we're going to define, so three things. So we'll call them chi0 of SF, this is going to be the dimension of H0 of y minus E F modded out. So the codimension, in fact. So really here what we're trying to measure is, well, how many global sections of F that are global sections on y minus E don't extend to all of y. And then this is simply going to be H1 of XF. And the local Euler characteristic, so this is what Wald defined, is simply the sum of these two things. And so Nils and I separate these things because that made the analysis somewhat easier. In some sense, I mean, okay, let me write a formula down and then explain sort of what these numbers might mean. So local to global, different kind of local to global than we're used to. Picture, yeah. Sorry, yes, thank you. Yeah, yes, great. Okay, so in this line that I'm going to write right now, we're back to the more global setup. So now I have this tau from YE to X capital S. Okay, so capital S. So this means L nodes. Okay, and there's a proposition by Blasch which very nicely relates sort of local Euler characteristics to global Euler characteristics. So I need F. This is going to be a locally free coherent sheaf on Y. And then F hat is going to be what happens when I take the push forward, but then I take the reflexive Hall, so double dual. Okay, and what Blasch showed for us is that if I look at the Euler characteristic on X for this F hat, well, this is basically the Euler characteristic for F on Y plus contributions from the nodes. So okay, where these are the these local Euler characteristics. And so in some sense, I mean, pretend that these don't say chi, pretend that these say H0 for a second. And so what this is saying in a sense is, you know, if you want to study something on Y, you might try to push it down to X. But then, you know, down in X, you might find things that are not, say, for example, linearly independent when you go back up to Y. And these sorts of local Euler characteristics can measure that for you. So why am I telling you all of this? How does this fit into our own picture? Well, so the punchline for us is that this H0 that we were interested in, so this H0 of X R1 tau lower star of Sm omega 1y, well, it's in fact equal to the number of nodes times the local Euler characteristic at any one of these nodes. And this requires an argument to show that this is true. But the point is that we can sort of boil down this computation of the H0 to one of these local Euler characteristics. And so, sorry? This is this local Euler characteristic of a node. Sorry? Yes. Yeah, exactly. It's just this chi1 bit. Yeah. No, that's right. It's not Right, sorry. So this is part of the reason that we sort of disengage these two things in Wald's original definition of the Euler characteristic. It's in part because we have to get rid of this bit. Yeah. So I really do mean just the part, the chi1 there. So okay. So this is how it's going to help us in the global picture. So now what we want to do is we want to understand how to calculate something like this in the local picture. So what's the okay, great. So back to the local picture. Right. Yeah. Why? Yes. I know. Yeah. Okay. So we're back to. Okay. So this is little s. So one node. Okay. And here the trick, sort of a key idea that goes back to Miyaoka is, well, the sheaf that we want to study is symmetric differentials on y, but we can also look at symmetric log differentials. So Sm of omega 1y log e, where, we're allowing sort of poles along e and a little bit more, of sort of simple poles along e and a little bit more than that. And then we're also going to put in a twist that says after I take all of these symmetric differentials, then I might allow some zeros along e. And you might wonder why you would ever do something like this. But the observation is that if I restrict to y minus e, well, these sheaves agree. So this A and this BH agree on y minus e. Because I don't have to impose anything on e. And so what that means is that when I push forward these sheaves and I restrict to x minus my node, these sheaves will agree as well. And so when I take reflexive hulls, then I can sort of complete my sections over that singularity because it's a codimension 2 thing. And so I'll get that TA double dual, T lower star, will coincide with T lower star of BH double dual, which is to say in the above notation that A hat will equal BH hat. And so that allows us to compute the chi of x A hat by replacing A hat with this BH hat. And in this BH hat, we can actually do a lot of local calculations and actually compute. That's the point. And so let me raise this and this one. And so the theorem so this is 119. Also, parts of this in slightly different formats appear in Jordan Thomas's thesis. So Jordan Thomas was a student of Bogomolov. Bogomolov was aware that some of the calculations in the original paper with Oliveira were not quite right, and he set a student to set the record straight, which he did in part, and sadly he left academic mathematics before he published his thesis. So the only way I know to get that thesis is to email Bogomolov directly. First thing is, if I take, so remember this A is the sheaf that we're interested in, we can calculate the chi0 contribution of A quite precisely. This is going to be 11 over 108 m cubed plus big O of m squared. Okay, so now we actually, I can write down the full polynomial, but actually the rest of this polynomial depends on m mod 6. There are 6 cases, so I'm not going to write that down, but we can do that. And this is actually where sort of the main mistake in the original Bogomolov-Oliveira paper is, because when they do their computation, they get a quarter here instead of an 11 over 108, which sounds innocuous, but in later calculations, there are subtractions that end up canceling out a main term that doesn't get canceled out if this is the correct coefficient. And so the estimates start falling apart after that. So there's that. And then the other thing is we can calculate the chi1 of, chi0 of this BH, roughly. Or at least we can tell you when it vanishes. And so it vanishes when h is less than m plus 1 over 2. And the chi1 of s. So there's a funny tension here. This vanishes if and only if, so h has a bound in the other direction, m minus 2 over 2. So these individual pieces sort of vanish in different ranges. And when you put these two things together, seeing as the chi is a sum of chi0 and chi1, which are non-negative integers, this chi1 of a, of bh, sorry, ends up being 0 if and only if mh is the ceiling of m over 2. Okay, so that's the, this is actually sort of where a lot of the sort of gut combinatorial calculations of the project lie in. But I want to tell you instead what the conclusion is for the global picture, and then show you sort of concrete consequences for actual surfaces. Okay, so let me write down the conclusion for the global picture. Sorry? It's not the floor? Oh, probably. So, conclusion for the global picture is as follows. So we're back to the global picture. So I have YE, and I have my tau, which was the resolution, and this is capital S. I'm looking at L nodes again. And remember, X is a mildly singular complete intersection of general type. And okay, so what we're going to do is we're going to put together two things. So one is I'd like to compute this Euler characteristic. So this is what happens when I take the symmetric differentials on Y and I push them down to X, and then I take the reflexive hull. And what this says is, well, since on X I can replace A hat with this BH hat, this is just chi of X and this BH hat. And now I can use the Blasch's formula, and this will be chi of Y BH plus a contribution from the singularities of chi of S BH. But what this theorem is telling you is that this, this contribution will go away if H is equal to this floor. And so I can calculate this chi x of A hat by just calculating something like this. And moreover, so I can also apply just Blasch's formula directly for A and A hat, and then put everything together. So I have chi of X A hat. This is chi of Y of A, plus a contribution coming from the singularities of these local Euler characteristics. And so this we have now determined this is chi of x bh, or in fact, I can do it as y bh, don't need the hat. And so when I put these two things together, I can compute that the local Euler characteristic of a node, so these contributions are basically all in our context. So remember that wall has, this node can be, some normal analytic singularity on a surface. But we're looking sort of just a collection of very simple nodes. And so in our case, I mean, these contributions are just, number of elements in S times these local contributions. And so, and the number of elements in S is the number of nodes, which is L. And so when I put these two formulas together, I get that this is chi of y b floor of m over 2 minus the chi of ya. Okay, why is this great? This is good because just as before, with a t as result, I can calculate these Euler characteristics from a Chern class computation. So this will be a Chern class computation. Okay, and why is that good? Well, now we have the total local Euler characteristic of a singularity, but the first part of this theorem tells me exactly what the contribution, the chi0 contribution is. So when I take this quantity and I subtract that quantity, I'm going to get the chi1. And when I multiply that by L, I'm going to get my h0 that I've been looking for. And then that's it. So, okay, so let me move this up. And then I'll show you the okay, so that's the, So let me just write that very quickly and say, so therefore, so we know chi0 of SA, which means that we get chi1 of SA by taking the difference. And hence, you can compute this h0 of x r1 lower star of Sm omega 1. Okay, by adding up L times this chi1. So now I want to show you some slides to see what happens when we put everything together and we actually execute those Chern class calculations. So how can I? Excellent. So let me go directly to this thing. So while this is coming down, we can already see what's going on. So X is our surface of, okay, so rather than show you the complete intersection thing, let me take the simplest case. So a degree D surface with L isolated nodes, and we take our nice good resolution. Our conclusion is that this H0 that we were interested in was this Euler characteristic plus the chi1 contributions from the nodes, which are, it's just L times any one of them. And so we compute this Euler characteristic by pretending that instead of looking at a, this blow up, we're just looking at a smooth surface of degree D with in P3. And you can see, I mean, this chi is very negative, right? I mean, as soon as these D's are mildly positive, you're going to get a negative coefficient in front of m cubed. So the chi itself is very negative. And what happens is that when you start adding the contributions from the nodes, if you have enough nodes, then you might be able to overcome that negative coefficient of m cubed. And that's exactly what happens So after executing everything that I just told you, we get that the that should say a chi1 of the node is this expression in terms of m cubed. And so now I have to go back and take this quantity and add L times that quantity to it. And so there's going to be a coefficient of 4 over 27 times L in front of m cubed. And L is the number of nodes. So if the number of nodes is big enough, it's going to overtake the negative coefficient that I see here in front of m cubed. And so in fact, what we can say is that if L is bigger than 9/4 of d times 2d minus 5, then in fact, I'm going to get symmetric differentials. And once I have that, I can run the idea at the very beginning of the talk to bound the rational curves. So you might ask, where can you apply that? Well, so if you go to d is 6, so degree 6, this says we have to have 94 nodes. Sadly, Miyaoka proved that a surface of degree 6 can have at most 66 nodes. So there's just no surface that you can apply this to. And this is sort of one of the bugs that occurs in Bogomolov Oliveira, because the estimates are wrong. It appears that they can apply to some surfaces of degree 6, but you can't, sadly. But if you go up to 10, then you need 337 nodes, and you think, okay, that's a lot of nodes. But there is a surface out there that has degree 10 and has more than 337 nodes. And it's called the Barth Decic. I've written down the equations for it there. It comes from studying sort of a surface associated to symmetries of an icosahedron. It's quite nice. So the Barth Decic has 345 nodes. And so the conclusion is that the Barth Decic is algebraically quasi-hyperbolic, for example. And here is a picture. That's the Barth Decic. So of course you see spikes there. I mean, you should really think of them as nodes, right? There's sort of a cone that comes out the other end. It was just cut off at that point. So you can see for the minimal resolution of this Barth Decic, we can actually compute exactly what the bound is. And it depends on m mod 3. And you see the dependence there on m cubed. So you just want an m that's sufficiently big to give you something positive. And the first positive m is 160. That is a lot of symmetric. There's a lot of m that you have to put in there to see symmetric differentials. Okay, I bet you the bound that you can do better than 160, but it depends on understanding that h1 that we talked about at the beginning of the talk, that we bounded by greater or equal to 0. So it would be nice to improve this. It's a bit surprising. I mean, perhaps there's a lot of information in that h1, but I would have expected, when you say that the result was asymptotic and for m sufficiently large there are symmetric differentials, I kind of would have expected that, oh, you mean like m equals 2 or 3, right? Not really sort of an asymptotic thing like this. But this is the first time that we saw symmetric differentials. And I'll just finish with a couple of things. This is a surface by Alessandra Sarti, constructed in a similar way to the Barth Decic. It's degree 12, and it has 600 nodes. And so it falls within the parameters of the theorem. In fact, you can say that you have your m should be 28 in here. So you have symmetric differentials of order 28, in fact. And so this thing is algebraically quasi-hyperbolic. And this 28 is the first time that the bound becomes positive. But you see, when it becomes positive, it becomes big, right? And so finally, my time is almost up. Go back to the intersection, these complete intersections, and let's just say you have just all quadrics, okay? A complete intersection of n minus 2 quadrics, and suppose that you have a few nodes. What this table tells you is how many nodes you need to guarantee quasi-hyperbolicity, okay? And so you might want to apply that to some surfaces that we know, but you might get a little stuck. So you might want to apply that, for example, to the cuboid surface, the Euler's cuboid surface. This is a surface of general type that's a complete intersection of quadrics. So what it asks for is a rectangular box where every side, every diagonal, and the long diagonal are positive integers. Okay, and is there such a thing? So we whip out the Pythagorean theorem, And we see that such a box would give rise to a rational point on a certain complete intersection. And so you might, and it has a few singularities. It is, in fact, 48 singularities. But sadly, the result, it's too few singularities in this case. We're unable to use the result on the nose to say something. In fact, this thing is very negative. But not everything is lost. And I'll finish in 1 second. Because even though we can't produce symmetric differentials on the resolution, we can produce some symmetric differentials outside of the singularities that you see. And in fact, we can produce sort of a 13-dimensional space of second symmetric differentials. And we even write them down. There they are. Okay, so some horrific thing there. And here's the punchline. There's 13 elements right there. And I claim that those are regular symmetric differentials of order 2 on x minus the singularities. And you can still use this sort of information here to bound the locus of rational curves on the cuboid surface. You can use these two, or these 13 in fact, to prove, for example, that every single rational curve on the cuboid surface has to pass through at least 2 singularities. And you can do better than that, but that's sort of a result that I'm relatively confident on. And lastly, I'll just say that if you use that method of the very beginning, you can try to actually compute the closed subscheme where the rational curves have to lie. And you can try to estimate the degree of that closed subscheme. And this is where, for example, in the Barth Decic, a preliminary calculation that we have suggests that there are at most 1.8 million rational curves on the Barth Decic. Okay? So it'd be nice to actually know how many there are and improve that bound, but that's going to require improving that H1. So thank you.
Thank you. Any question?
So in the examples at the end, you produce symmetric differentials, but you don't explain how you sort of bound the locus where they vanish. I mean, to prove that there are only finitely many rational curves, you need to do something more, right?
Right, right. So I mean, the basic idea is, say you have 2 independent differentials, right? Then symmetric differentials. Then a symmetric differential, just like in the original picture, when you have a global section, that'll produce sort of a degree m polynomial in sort of every fiber of that. So we're on a surface, so now you get a P1 bundle, and so you have a degree m polynomial in each one of those fibers. And when you have sort of 2 independent symmetric differentials, that's going to tell you that those degree m polynomials on P1 are going to have a common root. And so you can use sort of a resultant to calculate sort of a coarse closed subscheme where those rational curves are going to be. But it is essentially just using that idea from the very beginning, replacing omega 1 with SM omega 1, and then the only difference is, since we're working on a surface, it's just a P1 bundle, because it's differentials are rank, so it's rank 2, yeah, sorry, a P, not a P1 bundle, a P m plus 1 bundle, right? So you have omega 1 has rank 2, so SM omega 1 has rank m plus 1, and so the P of SM omega 1 is a P m bundle, and so a section of the symmetric differential produces sort of a degree m polynomial, and then when you have 2 of them, you have to that imposes sort of conditions on the roots of those polynomials, and we write that down as a resultant. But I can explain more later on. Yeah. So.
Thank you.
More questions?
So a general philosophical question. My intuition would say that the more nodes, the simpler the surface becomes. That a smooth surface would be more hyperbolic than a nodal surface.
Well, I mean,
is that true? Or
I don't disagree with that intuition, yeah. but for the method of proof, somehow it's counterintuitive. It's the nodes that actually help you. Okay. The nodes start actually contributing back to global sections. So.
For instance, what do you think about the truth? Like for this, like for instance, this surface that was said to be the surface of degree 6. Like, do you think it actually isn't?
Oh, sorry. So following up, I had the same intuition of Felipe, and that makes me wonder. I mean, the proof gives you what the proof gives you, but in terms of what's actually true, for instance, that sextic surface that's no longer proven to be hyperbolic, do you think it actually is hyperbolic, or?
I think it is.
Okay.
I would guess it is.
Do you think it's true without nodes at all?
I think you can do so. I mean, you can try to do this sort of calculation on it. And Nils actually had a master's student compute some of these things and prove that, for example, any rational curve has to go through 15 of the singularities and compute some horrific closed subvariety. So he could actually prove the not quite quasi-hyperbolicity because he wasn't looking at genus 1 curves, but he was looking at genus 0 curves, and he could bound the genus 0 curves by sort of extending a little bit and allowing sort of symmetric differentials on, but you don't try to extend them over all the singularities. Yeah, so I think it is true. I just this method doesn't give it to you. So, yeah.
Other questions? Yes.
So can you show the table for intersections of quadrics again?
Yes.
Right. So I mean, the last column says 0. Yes. So in this case, you get it regardless of the number of nodes, or what's the?
Yes, I guess.
I was just wondering because you didn't mention it when you showed it.
Yes. Oh God! Now that you say it, yeah, I think that's actually okay in this particular case. So I mean, part of the thing is that when you look at this, remember when we made this Chern class calculation and we looked at surface of degree d? I mean, this 2d squared minus 5d is the result of some difference of Chern classes. It can be like k squared minus chi or something like that. And so it's actually, or maybe it's the negative of that. But if you sort of take a large enough complete intersection, then you can actually turn that coefficient positive. And so then in fact you don't even need the nodes. I think that's, yeah. Sorry, I hadn't thought about that in a while, but that's I think that was what's going on in there. So, yeah.
More questions? If not, let's thanks Tony again.